Hi everyone. In this video I'm going to calculate a couple of values for the amino acid histidine. What I find most interesting are parts B and C. What mole fraction of the enzyme will be active at pH 5.5, and C, what is the average charge on histidine at pH 5.5. The full problem is as follows. Suppose the protonated form of the imidazole ring of histidine, this ring here, is believed to be crucial in an enzyme's activity. Thus, the enzyme is considered active when the ring is protonated and inactive when not. Below are the different charge species, predicted by the given pKa values. A. What is the pI of histidine? Before we get started on the pI, I suggest listing the charge of each of these species. At very low pH, everything that will be protonated, or everything that can be protonated will be protonated. And so here's the charge of +2. And as we make the pH more basic, we're going to start plucking off these protons. If we cross over the first pKa value, I think that's the pKa for this carboxyl group. We deprotonate that to get the negative species here, or the negative functional group, and so now we are +1. The next pKa is the pKa for the side group, nitrogen, and so let's say we go to pH 7, that is basic enough to deprotonate this nitrogen here, and thus the species is neutral. And if we get even more basic, like pH of 10, we're on the basic side of this pKa, meaning that we will deprotonate this nitrogen and make that neutral, and the overall charge of the histidine amino acid is -1. The pI is the pH at which the average charge of the molecule is 0. And so the two pKa's that are important to find this neutral species is the two pKa's that are flanking the neutral species. And so we're going to pick up 6.0 and 9.2. This has nothing to do with the activity of the histidine. We just want to find what the pI is, just to have a base to work off of. And so this is A, and the pI, you're picking the two pKa's that flank the neutral species, and you're taking the average of those two numbers. Because it would make sense that somewhere in between these pH of 6 and pH of 9.2, somewhere in between those two pHs, we would have the predominant species be neutral. .6, and what that means is that at pH equal to 7.6, there are a couple ways we could say this. The average charge is 0, neutral, in other words. And the predominant species will have a charge of 0. Now, there will be some molecules that are -1, some molecules that are +1, so on average it's 0, and the majority of the species will be 0, neutral. Next, what mole fraction of the enzyme will be active at pH 5.5? Okay, we got to understand the setup, and it's saying that because when the imidazole ring is protonated, it's crucial to the activity of the enzyme. We will say that when it's protonated, the enzyme is active, and when it's not protonated, it's inactive. Well, where's the border for that? The border is right here at pH equals 6.0. Because at pH 6.0, which is the same as this pKa, what that means is that if I'm more basic, if the solution is more basic, I'd have predominantly the uncharged ring. But if the pH is below 6, below the pKa, then my sample, the rings are predominantly positive. And so this is where it's 50-50. So at pH equals 6, what that means is that we have 50% active, meaning the ring is protonated, and 50% inactive. And so you can imagine that if your pH is 5.5, that is on the acidic side of 6, so we would expect the majority. It's always good to kind of have a guesstimate as to what the answer will be, and the mole fraction should be greater than 0.5. Right? The mole frac greater than 0.5. Or you could say the percentage is greater than 50%. Okay. And so we want the mole fraction. And the mole fraction active. And so what that really means is that we have the active, which is, let's abbreviate it, histidine plus, when the ring is positively charged. And the mole fraction is part over whole. So the part that's active over the whole, which is the active plus the inactive. Okay. So this is not a, this is a mole fraction, or you could think of it even as a percentage. And so you would have to get both His plus concentration and the His neutral. Neutral meaning the ring is neutral. And so do you see how this is a percentage of the whole that is active? So where do we see something like this? We see this in the Henderson-Hasselbalch equation, sort of, right? The Henderson-Hasselbalch equation actually gives us a ratio and not the mole fraction or not the percentage. Let me show you what I mean by that. Henderson-Hasselbalch, pH equals pKa plus log of, in this form, it is A minus, but we don't have a species, we don't have a ring that's minus. So you could even think of this as the, maybe it's better to think of it as a deprotonated form, over HA, which is obviously the protonated form. So this is the equation that most students memorize, but it doesn't mean that your species in the numerator has to be negative. It just has to be deprotonated. And so we're looking at these species here. And let me put this here. So if we're on this side, we'll say inactive. And if we're on this side of the pKa, that we'll say active, meaning the pH is on the left or the right of this pKa. And so if we substitute A minus and HA, this is where it gets a little bit tricky. You have to realize that we really mean inactive, active. Right? The deprotonated, in this case neutral, and the protonated, which is positively charged. And so the active like that. And we could put brackets to represent the concentrations. So what numbers do we plug in? The pH is 5.5, and the pKa we use is not the PI, it's not this pKa, it's the border by which we determine whether the enzyme is active or inactive. So it's pKa 6. It doesn't matter what these two pKa's are, because once we're below 6, the majority of the ring is protonated. Once we're above 6, the majority of the ring is not protonated. And so it doesn't really matter what these edge pKa's are. They could be anything. And so the pKa that we're using here is 6.0. It's the border, right, between active and inactive, plus the log of that. Now let's simplify this a little bit so I don't have to write so much. His neutral over histidine positive. And so we're close, but we're not quite at the mole fraction equation, right? Part over whole. And also, we want the mole fraction of active, not the mole fraction of inactive. So we're going to take the inverse at some point. When you do the math, what's the math? Try to find places to save time. So we have 5.5 minus 6.0. And then what do we do with this? We take the, what's the antilog? On my calculator, it's the shift button log. Okay. Don't mess with the signs. You're just taking this, that value that we calculated and putting it into 10 to the, you want to do this in parts. So this is negative 0.5, I believe. Let's try this one more time. 5.5 minus 6. Okay, good. And that equals log of, your x. And so it's 10 to the negative 0.5 equals x. So I had that. So 10 to the answer, which is negative 0.5. Okay, 0.3, let's round to 2. So x equals 0.32. But that equals his over his plus. And so if we take the inverse, should we take the inverse? What's the easiest way? Let's try to take the inverse. And so when we take the inverse, at least we got the his plus on top. The active, right, on top. And if we do 1, oh, don't do that. 1 divided by that answer, that's the inverse. Interesting. 3.16. Is that true? Interesting. 3.16. I wonder if that's coincidence. Oh, it's definitely coincidence. And so we have 3 times more of the active than the inactive. But that's not a percentage, right? We have to take part over whole. And so you could imagine this ratio is that. And so your percentage, we're going back to this equation. Oh, my bad. I hope someone caught this. This is plus. The whole is that plus that. Huge mistake. 3.16 over 1 plus 3.16. So look what we get here. This is now going to be a mole fraction, part over whole. So 3.16 divided by that answer plus 1. Ooh. Mole fraction, 0.76. So that is the mole fraction of active enzyme. And that's what we predicted. Greater than 0.5. Active enzyme. Go ahead and circle that. Just as an aside, well, we could convert this into a percentage, and literally you could say 76% of the enzyme is active. I kind of like thinking about these as percentages. 76%, sorry, of the enzyme is active. Oh, right? At pH 5.5. So that's another conclusion. You know this symbol, therefore, that. Okay. Now part C is asking, at the same pH, what is the average charge? And so we know that at this point, the pH 6.0, the average charge will be in between +1 and 0, so it will be plus 0.5. But because we are to the left of this pKa, we should have more of the +1, and so the average charge should be more than plus 0.5. Do you see what I'm getting at? Again, if it was exactly, the pH was exactly 6.0, because we have half protonated and half not protonated, you're really looking at the average of these two, halfway between these two. But we're skewing more to the acidic side, so we would expect the average charge to be greater than plus 0.5. Let me show you how to do the calculations formally for part C. I think some of you can do this in your head, like you're understanding the connection between mole fraction and then now we're going to do average charge. Just as a reminder, we are here +1 and this is 0, but now our pH is a little bit to the left. pH equals 5.5. Okay. Because we know the mole fraction, we're going to use the mole fraction because that is the mole fraction of where the predominant species is +1, right? +1 here. So again, you're ignoring these species at the end. They don't really matter. And so we have 76% of the whole being +1. The ring is protonated. So we're going to do something very analogous to figuring out, remember the exercise where you figured out the average atomic mass of an element based on its isotopes? That was where you got the weight of one of the isotopes and you multiplied by the abundance. And so if I have a bunch of molecules that are +1, we know the abundance is 0.76. So the mole fraction is the abundance of the species that are +1. And then for the species that are 0, right, the mole fraction would be what? It would be 1 minus this. So that is 0.224. You know, this should equal 1.0. That's the whole. And so now we calculate what I like to call the weighted charge. Just like for isotope, you take the mass of the isotope times its abundance, and you have the weighted mass, and you add up those weighted masses to get the average mass. And so we're going to do the same thing here, and you can see the calculation is pretty easy. And so to get the average, and what is this? This is charge. So let's put a sign there. And this is now the average charge. Did I have to go through all this histrionics to get to this number? No. You could have realized that from here. If 76% is +1 and 24% is 0, the average, or the weighted average, would be plus 0.76. And so what that means, it makes sense because now your average is not 0, your average is not +1, it's somewhere in between these two, and because we're skewing a little bit more to the acidic side, it should be more than plus 0.5. More than plus 0.5. And that is now the average charge. The last part where we have to figure out the pH, okay, where we have 23% maximal activity, well, we got to interpret this correctly. What that means is that you have, if you're looking at the mole fraction, you have 0.23 percent. I'm saying this wrong. You have 23%, which is the same as 0.23 in the decimal form. That is active. His plus. Okay. And if it's 23%, that means 77% or 0.77 is inactive. And so we know how to use these numbers. We could use them in the Henderson-Hasselbalch equation. We don't have to do anything fancy like we did over here. Part over whole. No, the Henderson-Hasselbalch is literally the ratio of the two species. pH, just lower down, equals pKa plus log of the two species. And now that we've done this before, let's just automatically input his neutral, which is the inactive, his positive. Okay, we might have to take the inverse at some point. Okay. Oh, no. We don't have to take the inverse. We just have to plug in the correct numbers. pH is the unknown equals 6.0. We're using this pKa because it is telling us this is the pH where we have the division between active and inactive, plus log, and we literally just plug these guys in. So you could take the molarity ratio or the mole ratio. This is the mole ratio, right? And so we're going to have 0.77 on top. Yes. We expect more, right, of the enzyme to be inactive because it's less than 50% of the maximum over 0.23. And so what do we expect? If 23% is active and 77% is inactive, we'll probably expect the pH to be to the right of this pKa. And it might be a lot actually, because that's, well, I'm not going to try to predict that. All I know is going to be higher. The pH is going to be higher. It's going to be on the basic side. 0.77 divided by 0.23, log of that answer, plus 6. The pH is 6.5. And that makes sense. It's above 6.0. Circle your answer. Let's give another digit actually. 6.52. And that makes sense again, because it's on the, again, the basic side of this pKa.